Okay, let's go ahead and prove the cross product for vectors in 3 dimensions today. Okay, so the claim here is that if we define a couple of vectors, 3 by 1 vectors, or 1 by 3 vectors I should say, we'll say V as the vector with components v1, v2, v3, and we'll say W with components W1, W2, W3, that the magnitude of the cross product of V and W is by definition equal to the magnitude of the determinant of the vector, the matrix rather, ijk, v1, v2, v3, w1, w2, w3. Okay. And that this alternatively can be thought of as the magnitude of V times the magnitude of W times the sine of the angle between the vectors. Okay, this is of course provided that I is the unit vector in the direction of x, j is the unit vector in the direction of y, and k is the unit vector in the direction of z. Okay, so that's the claim. All right, where to start? I think what I'm going to do is, since we all know what a determinant is, this is fairly easy to compute, we're going to start here. Now, rather than manipulating this, we're going to manipulate the square of it. And then we're going to take the square root of that. Okay, and the reason why I think we're going to do that is because there is a trigonometric identity forthcoming for sine squared of theta, right? 1 minus cosine squared theta. Finding a way to equate this to this as it stands might be tricky otherwise, okay? So let's start by establishing the square the square of this side here, okay, this alternative definition. Okay, well, that of course is going to be the following. Okay, which of course is going to be equal to the following. Okay, which of course is going to be equal to the following. Okay, which of course is going to be equal to the following. Okay, and this right here is just the dot product. Okay, so let's zoom out one step. Let's establish the dot product here. I did prove the dot product in a previous video, so you can feel free to access that if you so choose. Okay, but the dot product between V and W is by definition, okay, V1 W1 plus V2 W2. Maybe zoom out even one more step. We're going to have a lot to write here today. V3 W3, but that alternatively can be thought about as the magnitude of V times the magnitude of W times the cosine of the angle. in between the two vectors. Okay, so that right there we are going to use. Let's also be clear that we have used the following Pythagorean identity here today. Okay, the most fundamental, shall I say, of the Pythagorean identities. Okay, let's get that boxed up. Also very important. Okay, so we use that from this step to this step. So I'm going to go ahead and now think about this as the following. Okay. Okay, very good. Let's go ahead and expand all of this. Okay, so this is just going to be okay. The magnitude of a vector is the square root of the sum of the squares of the components. Okay, so it's that squared, and I'm going to do the same thing here now. Okay, minus all of this, which we will expand in the next, shall I say, long step. It's going to take some energy, but we're going to get through it. Okay. Just checking that, making sure we haven't committed any careless mistakes here. Doesn't look like we have. Okay, so this is simply going to be the following. And this is simply going to be the following. Okay, and I will actually keep this as it stands for now, and we will distribute everything in the next step altogether. Okay, let's check that. Here we go. That's why we check. Okay, very good. Now, we're going to have quite a few terms here, but that's okay. That's okay. We're going to take and multiply this trinomial by this trinomial and get the following. Okay, and then we're going to be subtracting off this trinomial multiplied by itself. Okay, and that's going to give us the following. Okay. Okay, let's carefully check every step there and make sure we haven't committed any careless mistakes. Okay. Okay. expansion of the first product of trinomials looks good. That looks good. Okay, and what about the expansion of the right-hand side, the subtrahend part? Let's check that carefully. Looks good. That looks very, very good. I've checked that very carefully, and I think we are good to go. So clearly, v1 squared w1 squared minus v1 squared w1 squared is going to go to 0. v2 squared w2 squared minus v2 squared w2 squared, that's going to go to 0. v3 squared w3 squared minus v3 squared w3 squared, that's going to go to 0. And we are going to have the following. Okay, so we've accounted for those terms there. Okay, and now we have actually two of these. Okay, so it's going to be minus 2v1, v2, w1, w2. Okay, so this and this have been accounted for. And then we have minus 2 of these. Okay, v1, v3, w1, w3. Okay, those have now been accounted for. And minus 2 of these. Okay, so those now have been accounted for. Okay, and oh yes, okay, I see what this is. This is actually not that bad. Okay, this is going to give us here v1 w3 minus, okay, v3 w1 all squared. Okay, that's going to account for this. Okay, it's going to account for this. And it's going to account for this. Okay, now we're going to have v2w3 minus, okay, v3w2, all of that squared. That's going to account for this term. It's going to account for this term, and it's going to account for this term. Okay, very good. We are missing a term here, aren't we? v2w1 minus v1w2 all squared, yes. So the v1w2, that needed to be accounted for there. It was right here. So we just accounted for it. So we now have accounted for everything. Okay? Very good. So this is the square of the magnitude of the cross product. So to find just the magnitude of the cross product, we are going to take the square root of this. Okay? Taking the square root of all of this. Okay. All right. Let's now go ahead and simply calculate the magnitude of the determinant here. Okay, that should not be too bad. So the magnitude of the determinant of this matrix here is going to be the magnitude of I multiplied by V2W3 minus V3W2, minus J, and then it's going to be the quantity V1W3 minus V3W1 plus K, and then it's going to be V1W2 minus V2W1, like that. Okay, let's get that cleaned up there. Okay, very good. And that's simply going to be the magnitude of the following vector. Well, you have the first component is V2W3 minus V3W2. Okay, the jth component, okay, got to distribute this negative sign, is going to be V3W1 minus V1W3. And then the z component is V1W2 minus V2W1. Okay, the magnitude of that. And how do you take the magnitude of the vector? Well, you just take the square root of the sum of the squares of the components. And we're going to have exactly what we have right here. So that worked out quite nicely, didn't it? So that's going to be the square root of, and here we go. All right, there you go. Took a little bit of effort, but we got through it. Hopefully now you understand not only how the cross product for vectors in 3 dimensions worked, but also why the cross product works. Leave your questions, comments, and concerns. We are always receptive to any recommendations for future content. We love proven math statements, physics statements around here, anything we can get our hands on, quite frankly. So do not hesitate to submit your recommendations. Have a great rest of your day, and we will see you in the next video.